Welcome back. We're talking about spatial interpolation. Last time I talked about the surface technique, which is called trend, which fits a surface to all the points. It's a global interpolator, and so that's going to be approximate because it doesn't necessarily go through the exact locations of values for points. And inverse distance weighted, and that's the one that follows Tobler's first law, which says closer things are more related than things that are further away. So it provides heavier weights to points that are closer to the unknown location. Today I'm going to talk about a couple other methods. Remember, interpolation is the process of estimating values at unsampled points based upon known values at surrounding points. So we're trying to get an estimate of an unknown location, what the value might be there. Natural neighbor interpolation, that's the next method I'm going to talk about. And that has to do with using areas of influence. So you have surrounding points and it comes up with what are called Thiessen polygons or Voronoi diagrams, which produce polygons that have areas, and then the interpolation is based upon the amount of area that surrounding locations have that correspond to the new location. So I'll walk through this one step at a time. You start up with your known points, your input point coverage, and remember from terrain analysis in the last module, you can make that into a tin. And remember how that worked was you drew circles that circumscribed 3 points, and if there were no other input points within that circle, you made a triangle out of that. And you did that for all the input points, and you make a network of irregular triangles, a tin. So that's the first step. The next step is to bisect the edges of each one of your triangles. So here's an edge. I can make a perpendicular bisector to that edge. That would end up being what looks like this one right here. This, you could make a perpendicular bisector. That would be this one. So you bisect the edges and you connect the bisectors, and what you come up with are these Thiessen polygons. And what a Thiessen polygon is a polygon where any point that falls inside of a specific polygon is going to be closer to this point than to any other points. So in this case, here's a polygon. Any point inside of here, this will be the closest point to that. So that's the natural neighbor. Anything inside here has this as its natural neighbor. Okay, once you have this Thiessen polygon coverage, you can see that you have areas. So now we have points, but we have areas of influence where anything inside here is influenced more by this than any other point. Excuse me. So once you've made these Thiessen polygons for all your input points, you make a new Thiessen polygon for your unknown point, the point you're trying to interpolate for. So that's what this represents here. This is your unknown point. And then you apply weights to your surrounding points when you do the interpolation that correspond to the amount of the total area that that point's polygon occupies in your new Thiessen polygon. So in this case, this point will get a weight that's proportional to that amount of the total area. This point will get a weight that's proportional to this amount of the total area. So this point's not going to get very much weight because there's not very much area here. This point's going to get a lot more weight because there's quite a bit of area here. So you can imagine how this compares to inverse distance weighted, where it was all dependent upon how far away the points were. So in inverse distance weighted, this point and this point would have similar weights. This would have a little bit less weight because it's further away, but not that much further away. But in natural neighbors, this point is going to have a lot more weight because it has a lot larger area than this point. So that's the difference between those two. Here's the continuing example of Utah. This is the raster elevation model, the DEM, kind of what we're shooting for when we do interpolation. Using just the airports, we come up with this interpolation. So you can see that it's a relatively coarse estimating method for relatively coarsely spaced points, but you can imagine if you maybe had a tin or had locations that had barriers and those things I talked about in terrain analysis, you could force barriers into your analysis and get a better interpolation method with smaller amount of data storage. spline is the last basic interpolation method I'm going to talk about, and that applies what you can think of as a rubber sheet to your known input values. And so the way I like to imagine this is you take your input values and you imagine those as being like a bed of nails, and the height of each nail is the elevation or the value of that point. So you have a bed of nails that's not all at one elevation, but it's at a varying set of elevations, and then you drop a rubber sheet over the top. And so that rubber sheet is going to touch the nails, but it's going to have to bend and flex between the nails, and so you're going to get a smooth surface that will go through all the points. So it's going to be an exact interpolator, but it will overshoot and undershoot in places. So what it's basically doing mathematically is it's using a mathematical function to fit a curve locally to some number of points that minimizes the curvature in the surface. And you can specify how many surrounding points you want to include in your mathematical function, and it weaves those together and meshes those curves together so that they're continuous, so that you have smooth surface curvature. So that's a local interpolator, and it's exact because it's going through the existing points. But you can see that there are cases where it might overshoot some and maybe undershoot some. Two kinds of splines, regularized and tension. If I use the regularized technique, again I want this DEM, and I get this. And so the regularized, you can imagine it as kind of a thick piece of rubber that's on top of the bed of nails. So it catches the really high points and some of the really low points, but it's just kind of smooth in between there. The other type of spline is a tension spline, and that you can think of as kind of a thinner sheet of rubber, and you can see that that gets a lot more of the variation in the interpolation techniques. Okay, so you can see that these techniques that I've covered so far, the trend, inverse distance weighted, natural neighbor, and spline, all kind of do different things and give you different outputs, and they all depend upon the number of input points. And so the more points you have in your input data set, the better the interpolation is going to be. The fewer points, the less good or the less high quality your interpolation method is going to be. Next time I need to review some traditional descriptive statistics that you all had many times, but I'll review it again because before I talk about the last interpolation method, we need to talk a little bit about statistics, so you need to remember how descriptive statistics work. So that'll be in the next video.